Listen. Alyssa asks, can you go over the enantiomer question from the practice midterm? Yeah, I'm gonna have to pull up Blackboard because I can't remember which midterm I put up there. I'm gonna go extra time today because I started late, so I'm not gonna cut this short. Sources. All exams. The 2018 winter midterm or the 2018 fall midterm, Alyssa? Yes, Hannah, stereochemistry is the last thing we'll cover for the midterm, and we're not covering R and S, naming it. It's just, is this enantiomers or are these diastereomers? As I said in class, we're not covering naming. It's not going to be on the midterm. So the midterm, like this midterm is really it's a midterm of the fundamental concepts that underlie the rest of the course. So I'm going to wait for Alyssa to get back to me on exactly which midterm she's talking about. So I'm going to take Madison's question next. Can we do another one that's similar to that? Yeah, I guess we can. Just let me. I'm going to shut. Oops, no, wrong computer.
Also, with that question, would you be able to go over how we analyze the Z and E part? Because that's really the only part that's tricking me up.
Okay, so what you really want is, can we talk about Z and E? Right? Like not R and S, but Z and E.
Z and E, but still do the rest of everything.
Okay, so let's do. Oh. I am making this up on the go. I'm going to get my alphabeticals wrong. That would be tricky. Sorry, my wife's just calling me, so I'm just going to let her know that I'm in meetings. So let's say we had this question: 3E, 5Z, 2R, 2-iodo, heptene. And I guess it would be hept 3,5-diene. Sorry. Yes, this makes sense. Is this, Madison, does this kind of float your boat?
Sure, yeah.
Okay. So what I would do first is I would just sketch in a heptene. 1, 2, 3, 4, 6, 7. So my first step is just make sure I draw in all the carbons. Then just make sure you put things in the right place. So there's an iodine on 2. And there's a double bond on 3 and a double bond on 5. Now, I'm not saying if these are Z or E yet. I'm just putting the skeleton together. This isn't my answer. This is just my skeleton. Now, let's say we want to talk about. Let's say we start by trying to address this 3E issue. Okay, so if we take a look at carbon 3, carbon 4, there is a methyl group, a hydrogen. I always draw the trans first because I just do. It's just the way I think. And then a continuation of the carbon chain. I'm going to use R, meaning carbon chain. It's just like a placeholder. Because what I'm looking for with these double bonds, right, is all I'm looking to compare is the things that are on the same side of like attached to one carbon, and the things that are attached to the other carbon. I'm trying to compare the different weights. So in both these cases, I just have hydrogens. I have hydrogens on all the carbons. So the first thing I need to do I'm going to call this line 1, I draw that line, and on both sides of that line, I assign which one's heavier. Well, the carbon chain is heavier than the proton. Whatever the carbon chain is. Like you can draw the whole thing if you like, but you come up with the same answer. Then once I've done that, I draw line 2. And I try and figure out, are the ones on the same side of that line or on opposite sides of that line? And they're on opposite sides of that line. So what I've drawn is an E double bond. Because the ones are not on the same side of the line. They're not, the ones are trans to each other, so it's an E double bond. The biggest groups are trans to each other, so it's an E double bond. And let me just rephrase that. The highest priority groups are trans to each other, so it's an E double bond. It's not about size, but priority. Are you with me?
Yes.
Okay. So now let's take a look at carbon 5. Let's just worry about these before we redraw it. And so again, what I have is a CH. On carbon 6, I have a CH3 and an H. And on carbon 5, I have an R and a hydrogen. Again, I could draw out the whole chain instead of R, but it's a carbon chain. It's heavier than hydrogen. And so if I do that, again, what I've drawn here, the highest priority groups are trans to each other, so I've drawn an E double bond. But 5 is not E, 5 is Z. So this is the wrong double bond. So what this needs to be is that, because that's Z. Here, the two 1 groups are cis to each other, and they're on the same side, so it's a Z double bond. So if I go back to this and I take this information into account, three and 4 should be an E double bond, should be the two big groups trans to each other. That's what I've got. But 5, the two groups need to be Z to each other. The 5-6 double bond. Then if I'm looking at carbon 2, I know that the 4th thing on there is a hydrogen. And if we look at that, I can arbitrarily check what happens. I'm just going to expand carbon 2, and I'm just going to think it's easiest for me to name it if I stick the hydrogen in the back and just arbitrarily try this, and let's see what we get. Whatever. I'm just going to erase this and give myself a bit more space. So if I'm trying to give priority to this, what's the highest priority group on this carbon?
The iodine.
Right. And the lowest priority group?
Hydrogen.
Right. Those are the easy ones, right? But try and wipe stuff out. Like if you can easily isolate things by which atom it is, do that first, just to simplify your logic, because then you're not trying to balance more things. Now we're just trying to figure out 2 versus 3.
The methyl group would be 2. I mean 3, sorry.
Right. See, yeah, that's why it's good, right? Because the methyl group is lighter than the other one's got more carbons, right? You're going to get a carbon attached to a carbon. The methyl group, the best you're going to do is a carbon attached to a hydrogen. So that's your order. We go 1, 2, 3. It is clockwise. That is R. It told us it should be R. So I just do that. Now, if it come out as S, I would just put the iodine in the back. To get the R. So does that make sense as a set of steps? I don't know if that helped.
Yes, it did. So
Yeah.
if it was supposed to be an S, couldn't you just switch the iodine and the hydrogen, right?
Yeah, exactly.
Okay.
Exactly. Like, it's once you figure out what this is, you go that like if this was supposed to be S, and I solved it and went R, I went, okay, no problem. I'm just going to put the iodine in the back. Now it's S. Because if it was in the front, it was R. So if it's in the back, it's S. Because I'm switching the iodine and the hydrogen. I'm going to do that one switch thing. So you switch the enantiomer.
Okay, thank you. That cleared some stuff up.
I'm glad. Okay, I don't know. Who was next? Megan did send questions by email, so I'm going to at least get to one of Megan, because those came in a little bit. Those came in earlier this morning, so she does have priority. Which one do you want to do, Megan? The first one. Okay, so Megan asked a question on B, C, and D. Okay, so let's say we had I made a mistake drawing it. Didn't make any sense. So we had this molecule here, and I ask you what is the most acidic proton on this molecule. So the most acidic proton on any molecule is the one that gives you the most stable other product. So in this case, everything is neutral, which is good first thing to check. And then we can start to figure out what happens. So if I remove this proton again, S minus, that's okay. If I remove this one again, O minus, that's okay, but not as good as S minus because S stabilizes a negative charge better than oxygen does. If I remove this one, again, N minus, and that's not as good. S minus is better than O minus is better than N minus. So the most acidic proton on a molecule I drew would be the SH, because any of the others would give you a less stable negative charge. The next question after that, I like this one a lot. Asked, which is the most acidic proton on this molecule? Now, why this is a bit of a trick is because we need to think about what we get on the stability. So the immediate thing to jump to is like, well, shit, it's one of these H's on the oxygen because then I'll get a neutral oxygen. But what's the, if we're thinking, especially where we ended last class, what is the least stable charge there? Is the O plus or the C plus? Yeah, C plus, because it doesn't have its full octet, right? So the O plus has its full octet. C plus doesn't. So what we want to focus on is making that C plus not plus. And if we remove that proton and we get a negative there, a negative next to a positive. That's got a resonance, and that's a lone pair, right? Because that's what you get when you take off a proton. That generates a new double bond. And we've just neutralized that C+. Again, as I said, assignment questions harder than test questions. But when you see that, you go like, yeah, of course, that makes perfect sense. It's hard to see. And there's no hydrogen on the other side to remove, so you don't have an option there. The final question in this series is a really stupid. This molecule does not exist. It is a really dumbass molecule. And the question basically asks you, which of those protons should we remove? And you want to remember, so this question basically comes down to what stabilizes a positive charge bigger, a bigger atom or a smaller atom? Because they're in the same column. And positive charges are stabilized almost always by the opposite of what stabilizes negative charges. So if you remember that bigger atoms stabilize negative charges better, you can remember that smaller atoms stabilize positive charges better. I'm really glad. So this was the one error that was the biggest error that was in the first edition of the textbook that we're using. They got it backwards. They said the bigger atoms stabilize positive charges better, and then they were eating crow about that as the authors for a long time, and it was a lot of fun to make fun of them for that, because it was but you know, it's just one of those things where it slips by people. So smaller atoms stabilize positive charges better. So then a question then becomes, which one is a bigger atom, iodine or bromine? Or which one's a smaller? You can ask the question either way, but iodine's the bigger atom. It's lower down the periodic table. We want the charge on the smaller atom. So if we remove that hydrogen, we generate a neutral iodine. We get that versus that. And having a charge on a smaller atom is better. So that means this is the most acidic proton. Megan, I might try and come back to your questions, but I'm just going to make sure that we get everyone to get to priority on something. So Hannah, you put something in the chat and you have your arm up. So how to draw electron energy diagrams for the hybridization of an atom. So let's say, you know, let's talk about an example. You'll have to tell me if you think that this is a fair example. And let's say I ask you to draw the electron energy diagram for this carbon. Is that a fair? Is that a question? Is that kind of the question you want to ask, Hannah?
Yeah, that was basically it. I was just going off of one of the midterm questions, and it was pretty simple.
So let's take a look. This is just carbon itself. Is this right? Four valence electrons, right? Like just normal carbon. Four valence electrons. Sorry. You're in agreement?
Yes.
Okay. So what we need to do before we do anything else, we need to figure out what the hybridization of that carbon is. First step. What's the hybridization of that carbon?
sp2.
Right. How did you figure that out?
Just because it has one double bond and 2 sigma bonds.
How many sigma bonds?
3 sigma bonds.
Perfect. There we go. Awesome. If you only had 2 sigma bonds and 1 double bond, you could be sp, because it's the amount number of sigma bonds that really defines you, right? So it's sp2. So we know it's sp2. So the electron configuration of an sp2 atom is three sp2 and 1 p, right?
Mm-hmm.
And so what you need in here is, if we're looking at the carbon itself, is only still got its 4 valence electrons. And since it's making bonds with each of these, it only puts 1 electron to each of those orbitals. Because if it doubles up any of those, it can't make a bond with that orbital.
Okay.
So if we're looking at the energy diagram of the so the question was, provide me with the energy diagram of the carbon atom in this molecule. This is the answer. You could also write, whether you write 1s or not, I would give it to you. You can if you like.
Okay. Yeah, that makes sense now.
Because if you put 2 electrons in any one of those orbitals, then it can't make a bond.
Mm-hmm.
Yeah.
Okay. Thank you.
Mm-hmm. Litsa.
Can you hear me?
Litsa, sorry.
That's okay. Can you hear me?
Yep.
Okay. Quick question about this one. Why did you put 3p?
Oh, because I can't.
Okay.
I meant it's 3 times sp2. I'm sorry.
That's okay. All right. I just had questions. I'll share my screen.
Yeah. I can stop sharing.
Okay. Don't mind this. All right. So I will go through my questions. My first question. Can you see my screen?
Yeah.
Okay. So I'm just making sure that. Yeah, please. Okay, this right here is not a stereo center because if we go this way and this way, it's the same.
Your microphone is really cutting in and out, and I don't know if it's because you're not pointing towards it or.
Okay, can you hear me now?
Yeah, you're quiet, but I'll turn up my speakers.
Okay. I'll try to talk louder. Okay, so first question is whether this and this is the same, so it wouldn't be a stereo center, right?
Right, because you get back to your point of origin before you reach a point of difference, right?
Okay. Yeah, that
You're
makes sense.
absolutely right. That is not a stereo center.
Okay, and then for number 2, this is something that I saw in the textbook, and they didn't clarify if this center fluorine or carbon attached to the fluorine is a stereo center. I'm not sure whether it matters, like, if, like, this was, like, hashed and this was, like, out of the page, would that make a difference?
You're absolutely right. It depends. It depends on what the other 2 stereo centers are doing, whether that's a stereo center or not. I think we can maybe get a little finicky here with words, and we all love fine distinctions. I think I'm okay with you saying it is a stereo center. Whether it is chiral or imbues chirality or can be named is difficult. And so I think if one of those centers is R and the other center
Like, if they had
is S, then you would have a mirror image of that molecule. And the mirror image of the molecule will be superimposable on that molecule regardless of what the center is of that middle. No, I don't think it's a stereo center.
Yeah,
I don't think under any circumstances it can be a chiral center.
Okay, yeah, I just didn't know whether it was a stereo center based on what we learned in class because like this was the same and like this chain is the same and this chain is the same. So I
yeah, and if one is R and one is S, they are actually different, but you would have internal planes of symmetry. And if both are R, they're the same, but the molecule is chiral. But I don't think it matters. I don't think you can name that middle one R or S if they're both R. There's no way to do it. I actually do not know the answer to your question.
That's okay. It means it won't be on the exam.
I won't. Yeah, no, I won't ask you that question.
Okay.
Now I actually do not know. I'm actually going to make a note of this, and I'm going to ask the hive mind what their opinion is, because I don't know.
That's okay. It was just in the textbook and I had no idea.
No, it's a great question. I don't know either. Ooh. Okay, the next one, we're not going to talk about this type of stereochemistry. That compound 3 is chiral, and it's because it's if you make the mirror image molecule of that, they're non-superimposable.
Yeah, this is a stereocenter technically, right?
Right. The whole thing is a stereocenter.
Yeah, because like, okay, yeah.
It's like a 3-atom stereocenter. The one on the bottom there is just misdrawn because you like the everything has to be parallel. You can't have the geometry drawn is not possible with one carbon, with 2 carbons. And then it's not a stereocenter. Because it's perfectly flat. Yeah, it has no 2-dimension. It has no 3-dimensionality. It's all in 2 dimensions. It's completely flat molecule.
But can't you switch these and create a stereocenter, or like create another molecule?
Yes, but it's not a chiral molecule. Then it's a diastereomer, like it's an E versus Z. And so they're not stereoisomers. They are stereoisomers, but they're not enantiomers, and so it's not a stereocenter if it can't generate enantiomers.
Okay, could you explain the definition of a stereocenter in terms of like chirality? Because I've been just following that, like if.
So a stereocenter is, I'm going to stick with atom, but your example number 3 breaks the atom rule. So I'm going to use the word atom just as a simpler way of saying a locus that can present things in different orientations in space. So I'm going to use the word atom instead of whatever the fuck this alien thing is. So a stereocenter is any atom that can put 4 things in different spatial relations to each other. You need 3-dimensionality. It needs to be a center. A stereocenter is an atom attached to 4 different things.
Okay.
And that's because if it's attached to 4 different things, there are 2 ways to arrange those things around that atom. And by things, I do not mean, in this case, things excludes lone pairs. When we were talking about formal charges and all that back there in orbitals, that things included lone pairs. Now things excludes lone pairs. So maybe I should say a stereocenter is an atom that is attached to 4 different atoms. Or 4 different chains that are made up of atoms.
Okay. So how come, because from the textbook I was reading, and they meant, like, they were going over, like, E and Z double bonds, and they mentioned that, like, it technically is a stereocenter. So how come this one is not? Yeah.
Technically, they are stereocenters because they are a place where you can arrange things differently in space. You can create diastereomers. I don't like, but there's an argument at the IUPAC right now, which is the International Union of Pure and Applied Chemistry, who make up all the definitions of things.
Yeah.
And depending which subset of rules you're currently reading, double bonds are treated as stereocenters or not as stereocenters. I'm going to restrain my definition of stereocenters to carbons. Okay. I think you do need to be aware that double bonds can be a place where you can get diastereomers forming, but I wouldn't count them as stereocenters.
Okay.
And if you count the number of stereocenters in a molecule, you would normally not count the number of double bonds in there as well. But double bonds can be a place where you can generate diastereomers because you can generate E or Z. Okay. Yeah. I'm sorry.
That's okay. It was just the textbook. There was a question that asked like how many stereoisomers or something, and they had us like they said that the double, like, to count the double bonds as a stereocenter and then include it in the calculation.
Well, yeah, if you're counting number of stereoisomers of a molecule, E and Z count as stereoisomers.
Yeah.
I just get very, very cagey about whether to count the double bond as a stereocenter. Yes.
Okay.
It's not either carbon as the whole system is a stereocenter.
Okay. Yeah. That's no problem. Okay, this one I saw in a video. I'm just making sure that these two they have an internal plane, but there's no stereocenters. So are they mesocompounds?
No, they're not mesocompounds because they don't have any stereocenters.
Okay. And that is
To be a
wrong.
mesocompound, you need to have stereocenters. You need to be able to assign RNS. You cannot assign RNS to those carbons.
Okay. And then here, this is something else from the textbook that I saw. Don't mind my comments of how flips. That's just my internal thinking. They said that these are a diastereomer, but these are enantiomers. And I was so confused over why, because it goes back to that question with like the F. Oh, I just realized that this is missing a. Okay. It goes back to that question with the fluorine. So like these two flip. So I would understand if we didn't count this and didn't count this as a stereocenter and say, yeah, they all flip, but why is it diastereomer? And then here, these all flip, but like it just doesn't make logically. It doesn't matter.
Okay, let's think about what, because I agree. So we were just discussing that middle fluorine, is that a stereocenter or not? And I went, you know what? I don't know. But what I would say is, if we look at the bottom molecule, for example,
Mm-hmm.
we can agree that those are mirror images of each other.
Yeah.
So, and can we also agree that they're non-superimposable?
That takes me a little while to
That's
figure
fair.
out.
So,
Yeah, so if I flip, yeah, technically you can't superimpose it because if you flip this one, like one of these will flip and it just doesn't match ever.
right, the fluorine on the right will be up, the fluorine on the down,
Yeah.
the left will be down, and the fluorine in the middle will be down. So it just won't it won't superimpose. And if we slide it over, we can get the fluorine in the middle to line up, but then the fluorines on the left and right don't line up.
Yeah.
Just slide it over, right?
Yeah.
So those are that's a non-superimposable mirror image.
Okay.
So by definition, it's an enantiomer.
Mm-hmm. Okay.
Now the top one is not a non-superimposable mirror image because it's not a mirror image,
Mm-hmm.
right?
Okay.
Like if you that one's a little bit harder to tell. That's not a mirror image, so we can flip it upside, flip it, left to right, and both the left and right fluorines will be coming out, but the middle fluorine will be going down. It's just not the mirror image, right?
Oh, I see.
But it's not the same molecule. So if it's not the mirror image and it's not the same molecule, and all of the atoms are connected to the same things, it's a diastereomer.
Mm-hmm. Okay.
So I think what this is answering is that middle carbon is a stereocenter. I think what we're answering here is it is. I just don't know how you would name it. I don't know.
Yeah, I think I was just going off of because I realized that to distinguish between diastereomers and like enantiomers or like chiral, achiral, I was looking at the number of flips, like if they all flip or if only like less.
And that's fine. And that worked here too. Like that works here. It's just that middle one's a little hard to say if it flips or not, because is it a stereocenter and should it flip? Right?
Yeah, because if we consider a stereocenter, then technically like here, not all of them flip, but if we consider it here, like not all of them flip. So I was confused with why they labeled it an enantiomer.
Yeah, I get you with that. I'm gonna fall back onto the. I think it's because that is a weird center, and it's not quite so. That I stand by that definition. What I'm saying here is I don't quite understand what that middle carbon is.
Mm-hmm.
I have no idea how to assign it RNS. I think I vaguely remember that if the two chains are identical on both sides, the one that is R takes priority over the one that is S. But that's actually only really, this is only really a meaningful stereocenter when they're both R or both S on both sides. And then it's really important which way that is. And I have no idea how to name it because in both cases they're both R, both the same. It's just I don't know.
Okay. Would we have to worry about like stereocenter?
God no.
Okay.
That this is fucked up. I do not. Yeah, no. No, I'm not doing this to you.
Okay. I feel bad. I've asked 5 questions, so if anyone else has any questions.
Yeah, no,
can-
that's a really good question because you're getting right at the heart of what these mean. So, and like I think we need to fall back, and when you run into that, we need to fall back on enantiomers or non-superimposable mirror images, and that's what we have in the bottom one, and the top one is not a super mirror image. So it's but everything's connected. It must be a diastereomer.
Okay. All
So
right.
I'm okay with their definitions there, but I'm not. I'm very shaky on why.
Okay. No problem.
This has never happened to me in real life, so I've never actually had to think about that problem before. It's a good question, though.
Oh, it's okay. If somebody else, I have more questions, but I know people have their hand raised, so they can.
Yeah,
go
so we'll make sure other people get their shot. So Alyssa, did I don't, you came up, I don't know if you got the answer to your question in that conversation.
Hi, I'm sorry. I had to take a phone call. I wasn't able to respond. I just wanted to see if you could maybe look at the one question on the practice midterm. I don't know if everyone has different practice midterms.
No, they're all downloaded from well, there's 2 practice midterms that I uploaded to Blackboard.
Okay, because
so I'm wondering which Blackboard, but because there's a 2018 winter midterm and there's a midterm from 2018 fall.
Okay, hold on one sec. Yeah, I think it's the 2018 midterm 1.
The winter.
Yeah. Let me just...
Okay. Yeah, I taught the class twice that year, once in the winter and once again in the fall. So I'm just going to download the winter one.
Okay, let me just find the question really quick.
Oh, there it is.
So it's number 11 on the midterm 1, 230.
Are the following compounds enantiomers?
Yeah, it's that one.
I'm going to just share my screen. I don't have my stylus on here, but we'll figure it out. Okay. So are the following compounds enantiomer? So what we're basically asking then is, what is the relationship between these molecules? And you have a bunch of ways to solve this. Like what you need to do basically is you need to rotate these things, right? Because what I'm actually going to do is I'm just going to sketch them out onto my stylus so we can sort of see the way we're thinking about this.
Like I was just trying to follow that flow chart that you made for us, and I was like, I don't even think they have the same connectivity.
They don't, and I think that I made them. They don't, so they're not. And I think I corrected this in person. Like, let's make it out. I think I added. I removed the double bond from the one on the left, because you're right, they don't. Okay. I just made a single bond. So
yeah, because if they don't have the same connectivity, they are not isomers or enantiomers, or right. Okay.
They're not enantiomers. They're not isomers even. They're not even they're not even isomers because they don't even have the same molecular formula, right?
Right. Okay.
Yeah. So I had to correct this in real time. I remember this question. You're bringing up all these traumas for me. So no, but you're completely right. So if I say that they are not, you're right. They are not isomers. Does that solve your problem?
Yeah, it does.
Okay. Yeah. So let's knock out the double bond, make it a single bond, and then you can maybe go from there.
Knock out which bond? Sorry, the.
I have is double bond there. Like the problem is I've got an extra double bond.
Okay, so the one on the right has an extra double bond.
Yeah, so remove that and make that a single bond instead, and then they are isomers of each other.
Okay, I'll be sure to look at that again.
Yeah, try it again. No, you're absolutely right. That question is unanswerable the way it is.
Okay,
I just right. It is. It's wrong. Yeah.
Okay, got it. So the answer is no.
No would actually be. No would be the first part. That would be so if I had left this as is, no would be the first part. Or any of the I guess, and you could name either compound to get the second half of the mark.
Got it. Okay.
And it's sort of an obvious longest chain. So going through the ketone and including the methoxy group.
Okay.
Like this would be your longest chain. I'm still showing this one.
Okay.
It's not necessarily the longest chain, but it's the one you would use to name because, no, it's also the longest chain because all the substituents come off here and you have the most oxidized components on that chain. So that's what you need.
The longest chain would be the one that is attached to the methoxy group?
Yeah, it is, right? Because it's 2 carbons if you go this way, or 2 carbons if you go this way. So that's tied.
Right.
But this one has a methoxy group, and this is 3 carbons. So total is 1, 2, 3, 4, 5, 6. So it's a hexane.
Okay.
And it's an one, a 2-one, because it's got the ketone, right?
Yep.
And and that would be 2. That would be given priority 2 because always give the most oxidized thing the lowest priority. And double bond is always going to win. So 1, 2, 3, 4. It's got a 4 bromo, 4 ethyl, and a 5 methoxy.
Okay, got it.
And then you need to figure out if this is RS.
Got it. Okay.
Yeah.
I had another question. I'm not sure what I'm doing wrong. I'm having such a hard time figuring out the formal charge for like nitrogens that are positively charged that have like 2 lone pairs or whatever. So like if I'll give you an example.
It's like, 2 lone pairs, not be positively charged.
Or sorry, 1 lone pair. My bad.
Well, if a nitrogen is positively charged with 1 lone pair, I'm fucking with you. And so it's not normally they'll have no lone pairs if they're positively charged. So let's take a look at a couple of examples. I promise not to do this on the exam.
Okay.
Like again, I'm trying to make you really think in here so that when you do the exam it's okay. So let's look at 2 examples of nitrogen. So you know what I'm going to draw. What I'm going to say is, okay, I'm drawing in every lone pair. Okay. No, I'm drawing in every lone pair that is present. So I explicitly say assign formal charge to N. All lone pairs are drawn. This would be a fair question.
Okay.
Okay. So if we look at number 1.
So it'd be positive 1.
Sorry?
Positive 1.
Yeah.
5 minus
right?
1/2 of 8.
Perfect. And then just change the color of my answers. Okay, if we look at number 2.
Yep, so 5 minus 6 minus 1/2 2.
5 minus 6, 5 minus 1/2 6.
Oh, right. Oops.
Right?
Or sorry, 5 minus 2 minus 1/2 6?
Yeah, sure. That's fine.
Okay, yeah. Okay.
Right?
Yeah, that makes sense.
Okay, and then this guy over here.
So it'd be negative 1.
Nope.
Oh, sorry, positive 2.
Yeah.
Okay. Okay, I don't know why.
Yeah, because you're under pressure because you're in public. That's why. You got this. You would not make this mistake if you were writing it. You just inverted things, right? Because lone pairs count for full value. Electrons in bond only count for half value.
Okay. Yeah.
Yeah. So yeah. So I think you've got this. I think I made a couple of mistakes in one of the midterms. I think we brought one up last class where it was like I wrote +1 and no, it was +2. It was this situation.
Yeah.
And so I think you're okay.
Okay. And then I just had one last question, then I'll let everyone else go. So like realistically, do you think that we're gonna have enough time to use our model kits to kind of like make models?
What I would do is I'd strongly recommend before the exam starts, you build yourself a cyclohexane.
Okay.
Just have a cyclohexane ready to go. You could also, if you want, have like just like a 2-carbon system for Newman projections with like, you know, 6 different colored balls on it that you can assign or have your balls ready. But I would just make a cyclohexane ahead of time, and I think you'd be fine. Yeah.
Okay, I just want to make sure because I'm still having a hard time picturing things without the model kit.
So yeah, I know this takes time. That's why we're trying to do. Often this stuff gets put later in the course. I'm moving it really early because we're going to practice it. We're going to keep practicing it. And if by the final you've got it, that's what's going to matter in the end.
Okay, all right, got it.
Yeah.
Perfect. Thank you. I appreciate it.
Yeah, like you know what? I think my policy is clear enough from all the times I've done this previously. So I normally don't announce before the midterm. But if you do better on the final than your midterm, your final mark replaces your midterm mark. If you do better on the midterm than a final, your midterm does not replace your final. But you get to count your midterm. So the midterm is a learning experience. If you balls it up, you're not screwed because the final can clean up. Because some of this, I get it. Some of this stuff is really freaking hard. And right now, it's like we've started a painting class or a sculpture class. I've talked to you about these concepts in sculpture, but I haven't let you touch the clay yet or do anything with them. So we're learning about all these concepts. We're not seeing them really applied to anything. And so for some people, you're going to need to apply them before it goes like, oh, that's why that matters. And that's how that fits. And suddenly it all makes sense. And so this needs to click by the morning of the final. And if it clicks earlier, great. But if it doesn't click until you've seen all the material in the course, that shouldn't count against you because we all learn differently.
Okay.
Anyways,
thank you.
Yeah. I'm gonna come back to Megan, I think. So Megan, what was your second favorite question of the ones you asked, or if you had something else that arose?
Yeah, can we do the second question I sent you by email?
Yep, opening up right now. Okay, so. Oh God, you want me to do number 5? Oh no, thank God. Okay, number.
Yeah, just number 7 goes with number 5. Just to explain the.
We haven't really talked a lot about reactions yet. So yeah, we haven't really done number 6 yet. Like we haven't really covered this, so we're not there.
It was question 7 for the reaction.
Yeah, but 7 relies on 6. And
Okay.
6 isn't something we've done yet. Like we haven't drawn that. Like I can do it if you like. So if we look at, because we haven't talked about hyperconjugation yet. But if we look at this one, and let's say somebody trying to get in touch with me. No. Because of hyperconjugation, we're going to, and again, I'm sorry, it's like I'm using a magic word. Because of magic, we're going to put the hydrogen there, or the positive charge there, which, sorry, I'm just going to see if this is urgent. Hey, I'm just going to Nothing is on fire. Okay. So we haven't started drawing these arrows. If you're ahead and you already make sense of these, great. If you haven't, great. It's not the end of the world. This is then asking for a reaction coordinate diagram. So starting material, intermediate, product. All reaction coordinate diagrams have a y-axis, which is energy going up. You can have a starting material. We're going to have a product. The product is probably lower in energy than the starting material. In this case, I'm pretty sure it is because we replaced a pi bond with 2 sigma bonds, and that's normally good. And we have an intermediate, which is a carbocation, which is high in energy because it's positively charged, and everything else on both sides is neutral. So we haven't done a lot of these. I think we sketched one out maybe on when we did acids and bases, but again, we haven't gotten into detail on this yet. So this would not be a fair question for a midterm.
I was just wondering what kind of questions can we expect for reaction coordinate diagrams?
Probably none on this midterm.
Okay. Thank you.
Because we just haven't covered them really, because we haven't really seen reactions yet. Like we've taken a look at some acid-base stuff, but that's it. So if this isn't today's problem, do you have another question about this, or is this like something I can put off till when we get to it?
No, that's okay. Thank you.
Okay. Yeah. Mohammed.
Hi, sir.
Hey.
Hi, I have this question that we had on assignment 2. I don't know why the equilibrium lies to the left and not to the right. I sent a picture in the chat.
So why does the equilibrium lie to the left and not to the right?
Yeah.
Okay. So how many charges are on both sides?
0.
Well, yeah. So there are but there are 2 charged species on the right. There is 0 charged species on the left.
Mm-hmm.
So does acetic acid? So normally you want to go for the fewer charges.
Oh, okay.
The other question to sort of check your work is, does acetic acid dissociate completely in water?
It doesn't.
No. So if it did, the equilibrium would lie hard to the left. But it doesn't. Or sorry, hard to the right. But it doesn't. Yeah. It tends to stay more or less like acetic acid. And this isn't acetic acid. This is butynoic acid, but same freaking thing. So it's because the charges kind of neutralize.
Okay, so that's why, because it's not about any stability or anything, just that it wants to stay as acetic acid because it doesn't want to dissociate in water.
Well, because it's more stable. Like what I've always been sort of saying is, hey, compare the charged species, right?
Yeah.
And the confusing thing is, there is no charged species on the left-hand side.
Mm-hmm.
That's a good thing. Not like the reason we don't compare the uncharged things is because uncharged things are really stable. So if one side, it's kind of like if I ask you to compare 2 piles of money, and one pile of money is $5,000, and the other pile of money is $2,000, and I say which one is more, you're going to say 5,000 is more than 2,000. In this question, and it's like that's because we count the amount of money, and one pile of money is more than the other. And what if I do instead is I put 5,000 on one side and $0 on the other, and I say which one of these is higher, and you're like, well, I don't know what to do here because I'm used to comparing 2 numbers, and on one there's nothing on it. So I don't know which one's more stable. It's like, no, 5,000 is more than 0. Like stability is all about stabilizing charges. So if one side has no charges, that guy's going to win most of the time.
Okay.
Yeah.
And how many questions are we having on the midterm?
No idea.
Oh, okay. All right, thank you.
I love how you think I've written it yet. No, I actually purposely really normally try not to finalize a midterm until I taught the last class, where I have like the last contact with the students, because what I don't want to do is I don't want to teach to the midterm, or teach to the exam. I don't want to have figured out what it is. I also, yeah.
Okay. All right.
And then I also don't let things slip. If I'm having a conversation with you guys going, I know there's going to be a question about this, so let's talk a little bit about more of this, because then I might give people who I have individual conversations with an advantage. So I try to leave it a mystery to myself until I'm done.
Okay, all right. Thank you very much.
Yeah. But it's going to be on the order of the other midterms, I'd say. Same kind of number of questions.
All right.
A little bit shorter, because I think I write my midterms a little bit long. Anyway, so I keep making them shorter. I still have Litsa, you have your hand up still. So we're back to you, I guess.
Yeah, okay, I'll share my screen and go back.
Okay.
All right, next question that I had was if all pairs of compounds have their stereocenters flipped, so we know that it's not a distereomer, how do we tell if something is chiral or achiral?
So if if all the stereocenters flip
Mm-hmm.
and the molecule is superimposable,
Mm-hmm.
what you're basically saying here is you have a mirror. If all your stereocenters flip, you have a mirror image.
Yeah.
Okay. So if all your stereocenters flip and your molecule is superimposable, that means it's the same molecule.
Then
Like if
yeah.
something is superimposable, then it's the same molecule. And if it's the same molecule, it's achiral.
Yeah.
Because
So,
the molecule doesn't have an enantiomer.
okay. What if you give us some complicated looking molecule and like we can't just rotate it in our head?
You know what? I think we had a question. Dea kind of asked a question like that up front when he. I think we had LSD down there, and what we were sort of like, he was like, okay, are these the only two stereocenters? And I was like, yeah. The only reason they wouldn't be is if you had some sort of crazy symmetry in the molecule.
Mm-hmm.
And we could look at the molecule and go, yeah, that's not symmetrical. Like it's just not. So if the molecule is not for a molecule to be achiral, it does need to have a lot of symmetry. It needs to be quite high order symmetry.
Okay.
And I'm not a mathematician, and I'm not really a inorganic physical chemist, so I can't talk about all the point groups, and let's not, because it's pointless. I'm just saying you need a crazy amount of symmetry. The molecules you have up right there, we were talking about those fluorine guys.
Mm-hmm.
You can sort of look at it and go like, shit, I think there might be some symmetry here. And the iodine molecule you have on question 4, there's like a lot of symmetry, right? Like you identified the mirror plane. Most molecules don't sort of have the symmetry. If you're looking at an achiral molecule, it's normally pretty small.
So an achiral molecule will have an internal plane of symmetry?
It has to.
Okay.
It literally has to.
Okay. All right. I just didn't know like what because I know you're not gonna give us like some just like a 1 carbon thing. We're probably gonna see something like a lot more. So I didn't know how to tell whether something's achiral or chiral because sometimes I just can't rotate it in my head to tell whether it's
I think the way you can sort of a molecule. So, and I'm not quite sure how to put this in words, but in an achiral molecule, I'll draw an example because I think this kind of summarizes the entire thing about achirality.
Okay, I'll stop sharing my screen.
Yeah, so I'm starting to share, so I think I've taken over from you now.
Okay.
This is almost the classic example. Like what for a molecule to be achiral and for it to have stereocenters. So this molecule has stereocenters. This is a stereocenter, that is a stereocenter. There's no question, right? Like this carbon is attached to 4 different things. Chlorine, a hydrogen, a CH2, and a carbon is attached to a chlorine. That's 4 different things. Same thing here. These are stereocenters. They are. So this molecule does have stereocenters. Its mirror image, though, it also isn't meso. Like, if I draw a mirror plane down there, it's not, there's no symmetry, right? Because it's on the bottom, that's on the top. But if we take the mirror image of it, we have that.
Is anything here like should there be hashed and Like hashed wedges and going out of the plane wedges?
Yeah, I kind of have it drawn 2D. So you know what I can do is I can, instead of doing it the way I've done it, I can do it that way if you like. That makes sense. I'll start saying that, like, hey, there's an up and down, but I completely see your point.
Yes, sometimes I can't tell when it's in 2D, which one's how.
No, I completely agree, and I'm very, very sympathetic to that. I'll try and stick with this because this excuses my absolutely horrible drawing. I can get away with stuff with this. Okay. So in this case, I think these guys are enantiomers. I'm looking at this, I'm thinking really hard about it, and it's non-superimposable. I can't get those to superimpose.
Yeah, like if you flip it, I'm just taking a look. Oh shoot.
Yeah, so this is not making the point I want to make. This is a simplistic version. So we have this guy. That's clearly the same molecule, right? Like it's a mirror image, but it's clearly the same molecule.
Yes.
You just slide it over, boom. But what we're seeing here and what makes this, so it's achiral. Because although these are both stereocenters, again, for the same reason the ones up there were, the molecule is achiral because its mirror image is superimposable on itself. So what we're doing is we need the symmetry, because for this to work, what we're doing is we're taking the mirror image of carbon 1, and we're going to slide that over onto carbon 2, because it's the same thing as carbon 2. We're taking the mirror image of carbon 2 and we're sliding it over onto carbon 1 because they're the same thing. So to do that, what we needed is symmetry between carbon 2 and carbon 1.
Oh.
So there needs to be this sort of symmetrical arrangement for this achirality to arrive. Like you need to basically you need to be able to slide. It's not that I'm putting 1 on 1 and 2 on 2. Like I draw the mirror image and hey, I can superimpose it on itself. No, I'm not doing that. I'm putting 1 on 2 and 2 on 1. And so I need a special arrangement between this carbon and this carbon. They need to be basically mirror images of each other.
Okay.
Otherwise, it doesn't work. So achirality needs this kind of sort of symmetry going on here. And if you don't have that, you can't be achiral. So as soon as I fuck with that in any way, you know, I stick a methyl group over here, I fucked with it, right? Now this is carbon 3, and now suddenly I can't do it because I can put 1 on 2, 2 on 1, but then 3 isn't on 3.
Yeah, and there's always one off.
Right. So I really need a super special arrangement of symmetry for this to work, for things to be achiral.
So it would be along the plane of the pentagon?
Yeah. Okay. So these guys, for example, now that I've added that carbon 3 and an extra methyl group, these are no longer achiral molecules. Yeah.
Okay.
Yeah. Door again. Sign up. Hey, quick thank you for last week. Oh, thank you. Yeah, again, thank you. I can't yell at the dean when he comes to knock on my door during office hours. Okay, what's next? I guess I'm available probably for another question or two. I don't mind going a little bit longer today.
I'm not sure if anyone else has any questions, but...
Well, then I'm happy. If no one does, I'm going to leave. But if not, you can go for another one.
Okay. I'm going to share my thing again.
Damn it, you got another one.
Oh, I have like 18. So if you host another office hours, I will be back.
Okay. You know what? I will post another office hours. I'll do the same time Thursday morning.
Okay. Okay.
Oh shit! I can't do that. No, I have to do a different time. I can do Friday morning. I'll be doing it Friday morning. It's more than 24 hours from the exam time. I'm good. Yeah, I'll do Friday morning.
Okay. I'm just gonna decide which one I'm gonna ask you. Okay, I'm gonna ask you this one. So this was just ranking some resonance structures. Don't mind this. I think you just forgot to include this resonance structure, but I was just wondering for these, like how you rank them. I'm confused with the hybridization part of it. So this positive charge, and this positive charge, isn't it located in p orbitals? Because that's what's moving and then creating the positive charge? Or
did I write it was in sp2 orbitals?
Pardon?
Did I write it was in sp2 orbitals?
Well, that's the reasoning you used for the ranking, so that's why I was confused. Like,
no, it's in p orbitals. You're absolutely right.
Okay.
No, you're absolutely right. It's in p orbitals.
So how would we rank this? Would we, like hybridization is the same, atom is the same. I know we didn't go over hyperconjugation, but
the hyperconjugation is different in these. So hyperconjugation is dependent on the number of potential parallel bonds.
Okay.
And so
because the way I ranked it is that I said this is number 1.
Yeah.
This is number 2, and then this. Sorry, I'm just taking a look here. This is the same. Okay, this would be number 3. But I used it. Like I don't think we learned this in class yet.
We haven't. I would not ask this question on the exam.
The fact that like it's just because carbons are electron donating, so technically they help to like neutralize this positive charge.
Yeah, exactly.
Okay. Okay.
It's a little bit more complex than that. We're going to discuss that, but that's fine. Yeah, you're right. I accept that. I'm fine with your answer.
Okay.
I'm not sure. I wouldn't ask it. I think I wouldn't ask it. I would accept 2 and 3 being inverted as well.
Okay.
But I agree with number 1 is number 1.
Okay. All right. I know you have to go, but thank you for answering my questions.
Okay. Thanks everybody. Chitra, I think you had a question which went up and I ignored it. In one of the lectures you mentioned we don't have to draw molecular orbitals with bonding, anti-bonding stuff. Does that mean there isn't any of that on the exam? Yeah, I want to introduce the concept right now because we're going to be discussing bonding and anti-bonding orbitals when we start talking about chemistry, because it's absolutely essential and there's no way around it. But right now we don't have an application for it, and so I'm not going to be asking you about bonding, anti-bonding, drawing those orbitals. I guess bonding, yes. I'm not going to ask you about anti-bonding orbitals. Do we need to know Fisher projections? God, no, Guntas. I'm never going to ask a question about Fisher projections. I hate them so much. And racemic solution stuff. So like the math stuff, Guntas? E and Z is naming, Dea. We're not covering naming. No, I'm not going to ask any questions about the math stuff. I've just decided it's not important. I'm testing your ability to plug into equations and whatever. Not interested. Okay, yeah. Okay. I think that's it, except for Melissa's unending stream of questions that we will address on Friday.
It's how I learned best. So.
No, I'm not making fun of you. I think you're doing a really, really good job with it. Your questions are great. I'm sorry. That could have come off as mean. I'm really sorry if it did. I think your questions. Okay. No, I really appreciate it. You're driving this, and clearly engaged. I think everyone who's showing up to these things, you're fine. You guys are going to be fine. But it's just, yeah. Well, we're going to see. This is an education for me, what happens when you flip a course and you take a look at the midterm. I have a feeling it's going to be a lot more these things are always really bimodal. There's a part of the class that just kind of comes out going like, I don't know what the big deal was. Everyone told me this was really hard. It was pretty easy. And then there's people who really, really struggle. And I think we're going to see that more so this year. And it almost always is, as I said, if you're doing the work, you look at the midterm and go, man, this wasn't bad. And if you're not doing the work, it's really tough. I'm not posting solutions to the practice midterms because I don't have neat solutions to them. Like I have massively messy, complex rubrics that I've sketched out somewhere and I think I've thrown out that we hand around to the GAs when they're marking. So no, they're for practice, and theoretically I might reuse questions from them. I'm not going to for this midterm. There's not going to be any questions reused from these, but in the future I might, and so I just don't really want the answers out there. Like, in 20 years, I'll probably reuse some of these questions. Okay. Take care, everybody. Have a good day.